Okay, well, thank you all for coming again. So let me quickly recap what I did last time. First of all, I gave you some general motivation, and I stated the main result. It had several ways of expressing it, one of them being that the stabilization map from top 6 to top admits a rational section. In particular, it's surjective on rational homotopy groups, which is equivalent to there being 6-dimensional Euclidean bundles over spheres that have non-trivial Pontryagin classes for arbitrarily high Pontryagin classes. And I just wanted to emphasize again, in case I didn't do it strongly enough last time, our proof is, and our approach is really an extension of what Michael did originally to produce these classes for some degrees and for some dimensions. And many of the key ideas that we are using are inspired by his work. Towards the end of today, probably tomorrow, there will be like a point where we differ significantly from what he does, which allows us to circumvent any kind of restrictions on dimensions and degrees. But this would have been never possible without the ideas that he had. Okay, last time we reduced the proof to the following theorem, which is slightly technical, but which does exactly what we wanted to do. I call it a bundle manipulation theorem for the purpose of this lecture series. The statement is the following. We take an arbitrary closed, two-connected, stably polarizable topological manifold. The dimension has to be at least 6. And then this theorem gives a recipe to manipulating M bundles. In the following sense, you start with a fiber bundle with fiber M, and we assume a little extra data, namely it comes equipped with a trivial disk bundle inside it. And then we define a new fiber bundle, namely E upper circle, which just cuts out this trivial disk bundle. So this is a fiber bundle with fiber M circle, which is M without an open disk. So that's a manifold now that has sphere boundary. And then there's a little technical addition that you can glance over, but I just wanted to say it because we actually need it. We pick a base point in the boundary of this disk. This induces a section of this bundle. And given this data, we produce a new bundle, and all the constructions that are resulting from the old constructions are indicated by a tilde. The new bundle is also an M bundle. It also comes with a trivial disk bundle, and it satisfies the following properties. Last time I stated properties in terms of kappa classes. These are stronger properties that imply the statements about kappa classes that I mentioned last time. First of all, we have not touched the underlying fibration. As fibrations, pi tilde and pi are equivalent, so there's a fiber homotopy equivalence between them. In particular, E and E tilde will be homotopy equivalent. But the additional property is that we have made the vertical tangent bundle to be much more trivial than the original one potentially was. Namely, if we restrict to the fiber bundle where we cut out this trivial disk bundle, then the vertical tangent bundle is rationally trivial, meaning that the classifying map to B top D is rationally trivial. And then the little technical extra that has to do with this section is that we can in fact choose a null homotopy that extends the given trivialization on the section that comes from this embedded trivial disk bundle. And yes, I forgot about that. That's very good. There is one condition here that I forgot, namely the vertical tangent bundle of pi, pi tilde, so after cutting out the disk bundle, has to split off a trivial plane bundle for some RD-2 bundle xi. Thank you. Okay, in the next 2 lectures I want to tell you about as many of the ideas and steps that go into the proof of this theorem. What I want to start with today is rephrasing all this data and all these conditions and conclusions purely in terms of classifying spaces, which allows me then to use essentially most of what Sander did in his first 2 lectures, or even 3 lectures, plus some more. If you set X to be the point, then a fiber bundle is the same data as its fiber. And this is an M bundle, and this is an M bundle as well. So for a point, it sends M to M. Okay. It doesn't do anything, exactly. Yes. All right. So let me start by rephrasing this result more in slightly more homotopy theoretical terms. So again, we have this embedded disk. We write M tilde to be the complement of this open disk. Now we have already last time we saw that there is a classifying space. I actually don't want to do this now. Here. I'm going to use this board for something else in a moment. Okay, there is a classifying space for M bundles. So maps into the space are the same as M bundles over the space I map into. And then there's also a classifying space for M bundles with the additional data of this trivial disk subbundle. What this is in terms of structure groups, it's a classifying space of the group of homeomorphisms of M that fix pointwise the embedded, the chosen disk. And this is simply by forgetting that I forget this disk. What this map classifies is I forget this trivial embedded disk bundle. This space I can also rewrite as follows. I can cut out the disk and consider instead homeomorphisms that are of the complement of the disk that are fixed on the boundary. This is an equivalence. One map in that direction goes by gluing in back the disk and extending by the identity over the identity, and the map in the other direction is by cutting out the disk. Okay, so just something that I said in words already. This here classifies M bundles. This classifies M bundles with an embedded trivial disk bundle. And this here classifies bundles with fibre, the complement of M, of the disk in M, together with the trivial, together with the trivialization of its boundary bundle. Okay. So what this theorem does is it takes a bundle that is classified by the rightmost space and it spits out a new bundle like that. So universally what this amounts to is the existence of a certain self-map of this classifying space. So we're going to construct a certain self-map which I'm going to call capital psi, from this space to itself. And whenever we are given then the translation to this result will be that if you're given a bundle, an M bundle with a trivialized disk bundle, that corresponds to a map from X into this classifying space. You can post-compose it with psi, and then you get the new bundle pi tilde. Okay, so what I'm going to do in the next few minutes is I'm going to translate these conditions and conclusions in this result to properties that I require on this map psi. So maybe I just write it down, what I said in words. This will classify sending an M bundle pi to the modified bundle pi tilde. Okay. All right. Now, as a little warning, in case you're taking notes, throughout this talk, I'm going to be extending a diagram that I start writing now. So you have to leave a lot of space around everything I'm writing on this board. Okay. So let's first re-express the condition that the underlying vibration is the same. What does this mean in terms of classifying spaces? Let me write the following. Here we have the space that classifies M bundles. Here we have the space that classifies fibration with fibre M. This is the classifying space of the topological monoid of homotopy self-equivalences of M. then we have the space that classifies M tilde bundle with a trivialized boundary subbundle, or equivalently M bundles with an embedded trivial disk bundle. And correspondingly here, we have the classifying space of the monodal homotopy self-equivalences of M tilde that are the identity on the boundary. So this here classifies fibrations, and this here classifies with fiber M. And this here classifies fibrations with fiber M tilde together with a homotopy trivialization of the boundary fibration. Okay. And then there are maps that correspond to taking a bundle and only remembering its underlying fibration. And when I say that pi and pi tilde are the same as M fibrations, what this means is that the self-map psi that I'm going to construct here will be covering the identity here. And in fact, it's going to cover the identity here, which is slightly stronger. So, conclusion, A is equivalent to psi covering the identity on the space that classifies the underlying fibration. And as I was saying, in fact, it will cover the identity on the space that classifies fibration with fiber M tilde together with the trivialization of the boundary fibration. Okay, so this is this first condition. So then let me re-express also in terms of the self-map psi the second condition B, which has something that has to do with the vertical tension bundle. So I need to put in the vertical tension bundle into this more classifying space style description that I'm pursuing here. And this one can do as follows. Let's write in between here the space that classifies M fibration together with an RD bundle over the total space. And homotopy theoretically, that is just the quotient of the mapping space from M to B top D by the group of homotopy equivalences of M. So this here will classify, maybe I use a color. This here will classify M fibrations together with a RD bundle over its total space. And that map is given by sending an M bundle to its underlying fibration together with a vertical tension bundle. Okay, I can do the same thing here. If I cut out this disk, then what I'm going to put here is maps from M tilde, M circle to B top. And this little subscript boundary here means that they are constant on the boundary of M, which is this sphere, which is the boundary of the disk that I cut out. And I divide out homotopy automorphisms homotopy automorphisms relative to the boundary of the complement of the disk in M. These maps are given here by extension by the identity. And what this here classifies is a fibration with fiber M tilde together with trivialization of the boundary fibration. And then I also have a map to B top D on the total space. This corresponds to the vertical tangent bundle, and this here is the constant map, and it also comes with the data of a homotopy that witnesses commutativity of this triangle up to homotopy. Okay, and in fact, I already messed up the diagram. I need more space in here, so let me remove that. I'm sorry. I'm going to put something in the middle here, namely. This here will classify, this will remember the vertical tangent bundle relative to the full boundary. But here, I'm only talking about the vertical tangent bundle relative to one point in fiber-wise in the boundary, which is relative to this section. So I have to write something different here, and I'm going to do the following. I'm going to write maps from M relative to partial 0, which I'm going to define in a bit, to top the modulo homotopy automorphisms relative to the full boundary of M. And what this partial 0 is the following. I'm going to consider M tilde, which has boundary a sphere, as a triad in the sense of Sanders talks. And in which way? Namely, I divide the sphere into the upper hemisphere and the lower hemisphere. And then partial 0 of M is the upper hemisphere, and partial 1 is the lower hemisphere. So how does that look like? I started with a closed manifold M. I cut out some embedded disk. That's the boundary of M. And now I divided the boundary into two codimension 0 submanifolds. Yes. Oh. Yes. Thank you. Okay. And the decomposition as a triad here looks like, well, let's write it that way. This here is partial 0, and this other part here is partial 1. Okay. Right. So what does this space here classify? It classifies fibrations with fibre M tilde together with, well, a trivialization of the boundary fibration, which corresponds to that I'm taking homotopy automorphisms relative to the full boundary here. Then a vector bundle, or not a vector bundle, an RD bundle over the total space. And then not quite a homotopy, a null homotopy of the composition, but only after I restrict to the partial 0 part of the boundary of M. Okay, this is what the space classifies. Okay. So what condition A and B in sum are equivalent to, if I ignore the rational part here, is that my self-map psi of the classifying space of M tilde bundle, M circle bundles with trivialized boundary bundles has to cover the self-map here that corresponds to fixing the underlying fibration, but setting this map here to 0. Let me write it here. Okay, so conditions, or like the conclusions, A plus B, and the B, let's do that for now non-rationally, are equivalent to psi covering the map that is the constant map on this mapping space modulo the identity on homotopy automorphisms considered as a self-map of the space, of this classifying space for fibrations with RD bundles of the total space and trivializations over partial 0. Okay. So this is our task. We need to produce a self-map of this space that covers this given self-map here, that sets this map to the constant map and keeps the underlying fibration. Does that make sense? Any questions so far? Pardon? For M a point, the conclusion is a trivial statement. Yeah. Yeah, because it's in fact non-rationally trivial. Because if I counter the disk, the tension bundle is trivial, if and only if it's stably trivial, and that's what I assumed here. Yeah. But yes, it's a good point. Okay, so how are we going to construct this weird self-map psi of this space? This is where embedding calculus enters. Yeah, that's the goal for the rest of today. Yeah, that's the juice. Constructing psi. All right. Yes. Also that will come in. I'm going to attempt to construct psi, and I will fail at multiple places, and each time I fail, I will collect an assumption. One of them being splitting off a trivial two-plane bundle. Another one being that I don't get to say that this is not homotopic, I can only do it rationally. It will come. We will not construct such a map, that's correct. We will construct a variant of this map, yes. Okay. Yeah. Okay, let me be more precise. First of all, I'm gonna need to have this assumption to be able to construct a map, and variant in the sense that I can set this map to be only rationally trivial, which in this picture corresponds to psi not covering the constant map mod the identity here, but I have to rationalize here. This is what I mean by variant, but I want to sort of do these things gradually, but maybe this is more confusing than enlightening, but we'll see. Just interrupt me and ask if anything is unclear. Okay. So now it's time to bring embedding calculus into this picture. Okay, so we are attempting to construct psi using embedding calculus. So the first thing I'm going to explain to you is how to express this space in terms of embedding calculus. Okay, what is the naive way one might try to achieve this? We could say, well, homeomorphisms relative to the boundary are the same as topological self-embeddings that are the identity on the boundary, and we could apply topological embedding calculus in the sense of Alexander's first lecture to the space of embeddings. And really there should be circles everywhere. But this is no good in the sense that this map here is not an equivalence. And I think you might maybe see a proof that this is not an equivalence in Sanders' next lecture. But as a sort of sanity check, we could check whether the condition for convergence that he mentioned in his last lecture are not satisfied. Namely, what was the condition? The condition was that the partial one part of the triad structure, which is the moving part, including into the full manifold as a tangential two-type equivalence. Here I'm fixing the whole boundary, so partial 0 is empty, partial 1 is empty, and the inclusion of the empty set into M is not a tangential two-type equivalence. For instance, any tangential two-type equivalence would be an isomorphism on fundamental groups, and this inclusion is not. So we're going to apply a trick which goes as follows. We say, okay, we're still interested in homeomorphisms of M tilde relative to the full boundary. let's instead weaken the condition on the boundary a little bit and just look at self-embeddings of m into m, m tilde into m tilde, that fix only partial 0, which was a disk in the boundary. So for instance, this would look like this. Here, this is a self-embedding. An element in here is a homeomorphism fixing the boundary. Here, we could have a manifold. We have this manifold. And for instance, look at the self-embeddings that fixes only partial 0. So something like the following would be allowed. I could move partial 1 of the disks inside. Okay, then I can apply embedding calculus with respect to this triad structure. And the claim is now that both maps 1 and 2 are equivalences. Okay. So let's think about this a bit. I mean, if one looks at this naively, this space of homeomorphisms fixing the whole boundary is quite different from self-embeddings where I'm allowed to do whatever I want on this partial 1 part. But in fact, for this is a consequence of two things, namely the Alexander trick, which is the fact that homeomorphisms of a disk relative to the full boundary are contractible, unlike diffeomorphisms, and the topological Pontryagin conjecture. Or rather, the solution of the topological Pontryagin conjecture. And deriving that one is an equivalence out of these two facts, I leave as an exercise. Okay, and now what about this map 2? There we can use this topological convergence result that Sander proved in his last lecture. Why is that? What was the condition in this topological convergence result? We reminded ourselves already of this condition here. The inclusion of the moving part of the boundary, which is partial 1, which in our case is the lower hemisphere of the boundary, into the source manifold, m tilde, has to be a tangential 2 type equivalence. And why is that? Well, because we assumed m to be 2 connected. So convergence of embedding calculus applies because partial 1 of m, which is the lower hemisphere, inclusion into m is a tangential 2 type equivalence because any 2 connected map is a tangential 2 type equivalence, which is, I think, one of the exercises in Sander's lecture notes. Is that right? Yes. Where I need 2 connected? I believe so, yes. Yeah, okay. Then it is not quite the only place. But the other place is something that is very technical that I'm not going to talk about in these lectures. Also because it is something that potentially with additional effort can be removed. But yeah, I don't want to go into this. Ask me in the discussion session if you're interested. Okay, so how can we proceed? Now we have this description of the space we are interested in terms of embedding calculus, and we can try to use embedding calculus to construct the self-map psi. Yes. Yes, exactly. The choice of, so the crucial point is that this is an equivalence is a very geometric fact about the Alexander trick, which is not true in an embedding calculus land. The Alexander trick fails for topological embedding calculus. Yeah. Okay, how am I doing in time? Okay. All right. Okay, now it's time to extend our diagram. We know now, okay, there's this embedding calculus approximation, which is an equivalence. All right. What can I put here? Or rather, let's put it here. I can go to the, I can apply one truncation, go to T1 of this embedding calculus, in this embedding calculus tower. And I'm going to explain this to you in a bit, but what I will get is almost diff space. I'm going to get the quotient of the same mapping space, but I quotient out homotopy automorphisms with respect to this triad structure. So they're only fixed on partial zero. Okay. So this map here comes from going from T infinity to T1. Or in the sort of abstract setting that Sander introduced, I can get this map as a restriction on path components of the following map. Here I put modules over the algebra in pre-sheaves given by partial zero of M in right modules over the topologically framed ED operand. Maybe I take reduced right modules. And here, this is an inclusion of path components of the core of the following category: spaces over B top D and under partial zero of M. And then this map at the back here is the map, for example, that featured in the smoothing theory result for embedding calculus that Sander mentioned. This is part of this functor on bordism categories, where here this is the corresponding core of the mapping category on the cospan category. Oh, sorry, on the cospan category of this spaces, or of this category of spaces over B top D. Okay, and these inclusions go the wrong way. Yes. All right. How does that help? Well, I already mentioned just now that this is the map that featured in a pullback, namely this smoothing theory pullback, that was about changing the way I frame the ED operand. This was the ED frame. This was the framed ED operand with respect to the map from B top D to B odd ED. But I can also now change the tangential structure to the identity on B odd ED. And then where I will land is in this so-called particle embedding calculus that Sander introduced. Which was the embedding calculus that was based on the identity framed ED operand. So this is a collection of components of the space of left modules over this algebra in the symmetric model category of right modules reduced over EDP, which was, in case you don't remember, so it's the co-limit of B odd ED included in the category of all operands. Or another way of saying it more classically, it's the semi-direct product of odd ED acting on ED. Okay, and then I can similarly go to the wrong truncated setting in this variant of embedding calculus. And where I will land is in the exact same space, but the target here is now the source of the tangential structure that I used, that used to be B top D, and has now become B odd ED. Because of this change of tangential structure from topological embedding calculus to particle embedding calculus. And this here lies as components in the core of space of the category spaces over B odd ED under partial zero of M. Damn it, I wanted to put this red. So there's a square at the front, which is a restriction to a collection of components to the square on the back that had to do with these right module categories and these over categories. Okay. Pardon? It is everywhere M naught. Yeah, in case there's an M somewhere, then this is a mistake. Thank you. Yes. Okay, does that make sense? Any questions? So what has happened? The upper part of the diagram was re-expressing my wishes in this theorem. Then I wanted to construct a certain self-map. I thought, well, I have a homotopy theoretical tool to study things like that. Embedding calculus, I want to use it. I discovered that with a smart choice of triad decomposition, I can indeed re-express this in terms of embedding calculus. And then I'm now faced with the task of constructing a self-map with certain properties of a space for which I know that it arises as a pullback. So this is why I wrote this bottom diagram, which came with the promise that the back face, this blue face, is a pullback by smoothing theory from embedding calculus, which was one of the main results of Sander's last lecture. Is there an arrow missing? Yes. Okay, I hope it is somewhat still legible. Let me, for increased legibility, remove things that are no longer necessary. That were intermediate explanations. Doesn't look too bad. Okay. All right, so this is a pullback. The front face is obtained by passing to certain components. So up to issues with pi 0 and the pi 1 that I'm going to ignore in this talk, this red square is a pullback as well. Okay. Now, what else do I want to tell you about this diagram? This map here is a very concrete map. It came from the change of tangential structure. So what this amounts to on these quotients of these mapping spaces is that this map is just induced by post-composition with the map from B top D to B odd ED. So star is induced by post-composition with the map from B top D to B odd ED, which is induced by the action of top D on ED that Sander was explaining in his lectures already. Okay. So let's remind ourselves of what we wanted to do. We wanted to construct a self-map psi of this space that covered a certain specified map here, namely the map which is constant on this mapping space and the identity on these homotopy automorphisms that I divide out. Okay, so let's suppose we knew that this map star is null homotopic. No, not the map. Sorry. Let's suppose we knew that the map from B top D to B odd ED is null homotopic. then we could do the following. We could say, well, I want to construct a self-map of this space. This space arises as a pullback. So what do I need to do? I need to construct a self-map of this corner, and they have to cover something here. Here's the self-map that I would use if I knew that this map is null homotopic. I would be the identity here. I would be the identity here. And here I would use the map that sets this here to 0, the constant map modulo the identity. And then this would induce a map on the pullback because of this null homotopy from B top D to B odd ED. Okay, let me write this out, I think. Where? Here, for example. So this odd here means automorphisms of ED in the category of operad, where I consider ED as an operad. And everything is happening in infinity land. So this is automorphisms of ED in the infinity category of operads. Yes. Okay. Let's see. What ED is. I think you know what ED is. Pardon? I can do it. ED was this operative little disks that Sander introduced in his lectures already. Yes. Okay. So what did I say? I said that if I knew that this was null homotopic, then could construct self-map psi of B homeo partial of M by using the identity on the particle embedding calculus part and the constant map modulo homotopy automorphisms relative to partial 0 on this mapping space. Mod H odd partial 0. Okay. And they would induce something on the pullback because the map star by this null homotopy is given by the constant map on the mapping spaces modulo, like quotient out by the identity on the space of homotopy automorphisms. Yes. So there are several technicalities that one needs to address. They make the paper more complicated than I would like it to be. Addressing these technicalities in this talk would completely blur what's going on, so I'm just going to ignore that. Okay? All right. So now there are two problems with the strategy, and we need to fix them. Problem one. The map from B top D to B odd ED is not null homotopic. And this is an exercise with the Euler class. That's the first problem. Problem two is if I construct psi in the way that I just did, then it would only cover the constant map mod the identity here. So I could only recover the fibration relative to partial 0 and not the fibration relative to the whole boundary. Because I cannot ensure yet that it covers the constant map mod the identity here. So there is a problem with the boundary condition. And this is a serious problem because, for example, to ensure that the new bundle has the same kappa class associated to the L class, which is something that I used last time very prominently, I need to know the vibration relative to the full boundary and not just relative to a part of the boundary. Okay, so these are two issues, and we need to address them. All right. Okay. Let me first say something about the first problem. And this is where this condition on splitting off a trivial plane bundle will really come in. So the condition that pi tilde splits off a trivial plane bundle says that the bundle I start with, pi, is classified by a map to a more refined classifying space than just the space that classifies M bundle with a trivial disk bundle. Namely, the following pullback. I look at, what do I look at? Here is the space that classifies M circle bundles with a trivialized boundary bundle. Then I can remember the vertical tension bundle and the underlying vibration. And I remember the vertical tension bundle only relative to partial zero. Then this condition corresponds to the fact that this bundle in fact is classified by a map to a pullback, where here I use the quotient of the mapping space to be top d minus 2. Just a space that classifies RD minus 2 bundle as opposed to RD bundles. So let's call this pullback B homeo relative to the full boundary theta, where theta is the map such that this map is induced by post-composition with theta. So this is just a double stabilization map from B top D minus 2 to B top D. Okay. Why does that help? That helps because now I can change this whole diagram to make all the occurrences of B top D into B top D minus 2 by taking suitable pullbacks. So let's forget the upper part. And the rest I change as follows. I add the theta here, which corresponds to putting a D minus 2 here and everywhere else. Right. Yes. So then the map that I needed to be null homotopic, that used to be the map from B top D to B odd ED, now is the map from B top D minus 2 to B odd ED. There's the composition of the double stabilization map followed by the canonical map from B top D to B odd ED. And it turns out that this map is a lot more trivial than before I did this trick with adding this trivial two-plane bundle. This was not a good idea. Okay. And what we prove in this direction is the following. Namely, we show that a suitable rational variant of this is indeed true. And then I'm going to explain to you why this variant is good enough for what we do. So the composition where I do the following. First of all, I change this map by restricting to orientation-preserving homeomorphisms of RD and orientation-preserving automorphisms of RD. What that means, I'm going to explain to you in the next lecture. In the second case, in this case, this is maybe maybe a bit more standard. But also that I will recall in case for those who are not familiar with what it means for homeomorphisms of RD, homeomorphism of RD to be orientation preserving. I'm going to recall it in my next lecture as well. So this is the orientation preserving variant that I just did, and then I post-compose it with the map induced by rationalizing the operant. So this is now the space of orientation preserving automorphisms of the rationalized ED operant. And the theorem is that this composition is null homotopic. Okay. So what does that mean? That means in my previous strategy, I can try to put myself in a setting where I only need to care about the rational ED operant. And doing that does not just involve rationalizing this whole diagram, but there are subtleties with rationalization that are kind of intricate that I'm going to ignore. But roughly the sort of statement is the following. If we use this null homotopy, we can construct a map psi that does no longer suffer from this first problem because we've solved that. There is still the second problem that the resulting map will only cover the constant map modulo the identity on this part of the boundary and not the full boundary. And we can do that after partially rationalizing this diagram. Okay, so the proof of this result I'm going to explain in my next lecture. And for the remaining 5 minutes, I'm going to start by explaining to you how to solve problem 2. How to save that we've forgotten more of the boundary than we wanted to. Okay. Oh. Okay. So what about the second problem? Forgot the numbering. What we want to solve the second problem is the following. We want that there is a factorization like this. Let's say we take homeomorphisms of M circle here, self-embeddings relative to the partial zero part here. Then we can go to the limit of the embedding calculus tower. I already explained to you why this is an equivalence. And finally, we can go to particle embedding calculus. This is also from M tilde to M tilde. Okay. Now, if I have a homeomorphism that fixes the whole boundary, then of course I get a homotopy equivalence that fixes the whole boundary. If I just have a self-embedding fixing partial zero of the boundary, then a priori I only get a homotopy automorphism relative to partial zero of the boundary. In fact, I explained to you that this map is an equivalence, so really I get one here. But if one didn't know that this map is an equivalence, then what I get is just a self-map of M relative to partial zero and not the full boundary. If we, then there is a map here that comes from the one truncation of this embedding calculus tower. Suppose we knew that this map that records the whole boundary factors all the way over this particle embedding calculus. If we have that, then we are done. Because what we can do is we could, in this whole diagram, take appropriate pullbacks using this map to make all of these partial zeros to partials, maybe fixing the whole boundary. For instance, how would this work here? We use this map, then map to the homotopy automorphisms relative to partial zero of M. Combine that map with this factorization to get a map into the pullback, which is exactly this quotient where the partial zero then became a partial. So what does that say geometrically? Geometrically, that says somehow particle embedding calculus still remembers that I can that M has a complement, that there is a different part of the boundary that is a priori moved, and something like the Alexander trick. No, let me not say it that way. I just want this dotted map, and I'm going to explain to you why this dotted map exists and how to get it. But I'm gonna give the proof of that next time. But I'll just state the statement that will imply this now. Actually, let me state that next time as well. I'm going to end here. Thanks. This one. So this comes from, so this is, another way of writing this would be, no, let me say it differently. We have this map in this tower that Sander was constructing. T1 of it was given by maps fixing the boundary of M times M that are over the under the tangential structure, so under B odd ED. And I can further forget that to maps to partial zero, to self maps from M to M. Now I'm realizing that I should have really put little crosses here, which means I pass to those components that are homotopy invertible, so that this composition lands in homotopy automorphisms relative to partial zero of M. So, for instance, if the P would be an O, then this would be automorphisms of this, and let's forget about the boundary condition, just to give you a sense again where this map came from. This would be automorphisms of this presheaf of embeddings of disks into M. And we can, by restricting to one disk, we get a GL, a a self-map of the space of embeddings of Rd into M that is equivariant with respect to the action by self-embeddings of Rd by precomposition. That space of self-embeddings, then explained to you, is equivalent to top D. So you will get an automorphism in particular of that space, but this space is equivalent to M itself. So this is sort of roughly how the underlying homotopy type of the manifold is remembered by its presheaf. So if we have an automorphism of the presheaf, we in particular get an automorphism of the underlying homotopy type. Yeah. Yes, okay. No, that's okay. I think I can just do one of the cases and then you can do the other one in analogy. So did I understand your question correctly? Why does the existence of this dotted map solve problem 2? Okay. I'm going to explain to you why with the dotted map I can put a partial here instead of a partial 0. Now let's do the following. Let's say we look at this space. Then that has, just like any orbit, has a map to the classifying space of the thing that acts. And the pullback along the map from the classifying space of homotopy automorphisms relative to the full boundary that forgets part of the boundary, the pullback are the orbits of this group acting on this. There's a circle everywhere. I'm sure I forgot a ton of circles during this talk. Okay, so now if I put B T infinity embeddings particle here, I can use the map given by one truncation here. I can use my dotted map here, and the fact that this diagram commutes will tell me that the compositions here agree, so I get a map here. And that I can do like with the bottom row, with the row and with the row above, and then this solves problem 2. Yeah? Okay, he's nodding. I take that as a yes.